Okay, so we said that it's a straight-through estimator, so it lets the gradient go through itself. But how? I mean, what is different about it? It's not just exactly straight through. It's not like an identity function, but it is different. So let's see this concept. The concept of a STE, abbreviated as STE, straight-through estimator, is that you set the incoming gradients to a threshold function equal to its outgoing gradients. So an incoming gradient comes, when you threshold it, and you just provide it, and disregarding the derivative of the threshold function itself, which is 0. Well, when we are doing this, we use something called an indicator function. Guys, indicator function is nothing. If you see this notation, don't be fooled. It is not indicated like this. It is a fancy way of saying thresholding. So just you don't say threshold. If you want to put thresholding in mathematical notation, you use this indicator. The indicator function is very simple, which means as long as x belongs to A, so the condition A holds, this is going to be 1 or other 0. So which means this is the original derivative, incoming derivative, so it's incoming derivative. This is the straight-through estimator. So what we do is we multiply it with some values, with 1, if this condition holds. If this condition does not hold, you feed 0. So you let some part of the gradients, depending on the value of R being the output of that layer, forward output of that layer. So as you can see, GQ is the original derivative coming in, and GR is the straight-through estimator, our estimated grade, and this is the formula. What is that formula? Let's get into the details. We said that the indicator function is 1 if this condition holds, if it is 0 if it does not hold. So the forward pass is this. So we are trying to construct the binary layer. Forward pass is the signum function. That's okay. In the backward pass, instead of the gradient, we use straight-through estimator. So I'll make some simple definitions, guys. So let gy be the incoming derivative from right. So I'm going to calculate the straight-through estimator to calculate this guy, right? Is the theoretical derivative we need, right? We are going to calculate with ST. So by ST, what we do is we element-wise multiply gy with this value being the indicator function. It is 1 as long as this holds. It is 0 if this does not hold. What is it? The absolute value of z, this z being the input to this function. If the input to this function has absolute value smaller than 1, then we feed the gradient. If it doesn't have, if it is larger or much smaller, I mean, if the absolute value of z is more than 1, the gradient is 0. So what we are trying to say is, as long as the actuations are within this boundary, we'll let the gradients in. If the actuations go higher, we stop the gradients. It is like suppressing the activations within a boundary. And we element-wise multiply it. So the gradient passes through, but some of it passes through, depending on the value of the z. So ST is like a gradient going through straight through a hard 10H, because actually this function is similar to hard 10H function if you just go and check it. It is that simple, guys, nothing else. Anybody who can add a layer to any framework, being MATLAB Deep Learning Toolbox, or be it Python, some other library, you can write this function. Actually, this function is already written for many Python libraries, but for MATLAB Deep Learning Toolbox, you can write it. And you can train your networks. You can try it, by the way. That would be another good way to test it. Okay, let me continue. So we understood what the binary layer is. We have the binary layer now. Our plan was to put a binary layer so that we'll be able to train the binary network, right? Okay, we've got the plan. So we have an estimator for the gradient. So we now know the forward pass and the backward pass of the binary layer. We can construct the binary layer. Okay, if you check, please check the original paper, guys, by the way. It's a very nice paper. It is explaining everything in detail related to it. So this is the stochastic part, but before that, the binarized neural networks, this paper. Just read this. These are very good papers on binary neural networks. If you are going to do binary deep learning, these are the papers that you must read. Okay, so we come back to the forward pass. This was a pseudocode I've shown earlier in these week's videos, in video 2 or 3, I don't remember, in the previous videos. So let's remember this formula and understand it better. So it is like a simple convolutional neural network. The assumption is that there's a convolutional layer, there's a batch normalization layer, and there's a ReLU layer. You can change this. But this is a very, very common architecture. So we are keeping this architecture for now. So the pseudocode for this architecture is, in which case the C is the cost function. We don't have C in the forward pass, but we will have. L is the number of layers. Sk is the activations before batch norm. So it's the result of the multiplications. Okay. Ak is the activations after the batch normalization. And you binarize them and you get applied to ReLU. So please note that when there's subscript B, it means the binarized version of this one. So ABK is the binarized version of AK. AK is not binarized. So this is not binarized, this is not binarized, this is not binarized, but since there's B here, this is binarized. So it's simple as that. So what is the pseudocode? Well, for each layer from 1 to L, you binarize the weights. Using the binary activations, you use the multiplication. Actually, this is XNOR operation, as we talked about. But you sum them up. When you sum the results of XNOR operations, many minus ones and plus ones, the result can be -2 or +7, depending on the number of summations you do, right? Well, that's why Sk is not binary, because you sum these up. These are binary, but this is a matrix multiplication which sums the multiplications. This is not binary, so there is no B. You apply batch normalization because there's batch normalization layer. In case theta k is the parameters of the batch normalization layer, you get activations which are still not binary. We are not still binary. So if this is not the last layer, if they are hidden layers, we binarize them and we provide ReLU. That's how you do the forward pass. But in order to be able to do the forward pass properly, you need to do the backward pass in training as well. So what is the backward pass? So remember guys, VK is always non-binary at every iteration. We binarize it to forward pass. So what happens is, at every iteration, we have WKs as non-binary during training iterations. In the end, we'll have binary values. But during iterations, the backpropagation will feed us non-binary values. How? Let's see the backward part. Before the backward part, let me just point to an important stuff. So as you can see, if you don't have the B subscript, they are not binary. That's why Sk and Ak are not binary. Sk is the multiplication of binary values, but it does summation as well. So its value is not -1 or +1. It's -8, +8, as I said in the previous slide. It's not binary, and we keep it that way during training. And we feed this to the batch normalization, which is not binary. Parameter is not binary. We obtain a non-binary value. Then later we binarize it. So, okay, in training we binarize these values, but this does not necessarily mean that we do not keep the non-binarized values. We keep them. During training, we keep the non-binary values as well, because we continuously binarize them. That's why the binorm operation is non-binary, and the activations are kept non-binary temporarily before they are finally binarized. This doesn't change if the binarized operation is deterministic or stochastic, but we are doing, for binarized operation, the signum function in our case. We are applying the signum function. Okay, now, the backward pass.